So in this video, we're going to talk about a bit more advanced fields. We're going to talk about gravitational potential. And I suppose it's a good place to start from equation, like a thought process. So say for example, we've got our Newton's law of gravitation, G(m)(m) over r squared. It's a great place to start because a lot of all the other equations are going to come out of this. So we can actually rewrite this equation based on what F is. So we can say that F is equal to mg. So it comes out Newton's second law, F equals ma. So we can say m times g is equal to gm m over r squared. And what's quite nice about this is we can then actually say, well, what is energy in a field, potential energy in a field? Well, we have the classic GCSE term that GPE is equal to mgh. And mgh obviously is the distance from the center, often written as delta H. So GPE is equal to mg delta H, where this then kind of comes from a more scientific point of view, that you can have an amount of potential energy at a distance h from the center of mass. You have this mass, this is the mass here, a distance h from center of mass. Well, if you notice, that's actually like a radius, so r. So actually we can rewrite this to be GPE is equal to mg r. And quite nicely with that, we can then sub that in over here. If we times both sides by r, we get mg r is equal to gmm r over r squared, which hopefully you'll quite nicely see here that we can get rid of these r's to leave us just one r left over, and we end up with, well, we can rewrite this as mgh or mgr, doesn't really matter, but it's still GPE. It's the actual potential energy that it's got there, gravitational in this case, is equal to gmm over r. Well, that kind of seems like a lot of work just to get rid of a term in some respect, but this at least it shows you where that equation comes from. The fact that if we have, if we want to know the GPE in a radial field, so remember a radial field in terms of the Earth looks a bit like this. And remember, I've got a whole series of videos about radial fields, explaining fields, etc., etc. So it's really good if you want to go back and have a look at all that stuff. So this is basically telling you at a distance of r from the center of mass, you have got an m here and an m here, and those are the two m's there, and we've got a distance r. This gives you the actual energy stored by that mass at that point, the potential energy that it actually has in a radial field, which is a really useful equation. So we're going to take that equation, and I'm going to use a new sheet of paper here. I'm going to take that equation and do something else with it here now. To introduce you to potential, because actually all we've done so far is gravitational potential energy. What I want to introduce you to is gravitational potential, so otherwise known as Vg. It's usually the term for it. Grav potential. So you might be asking yourself, well, how is gravitational potential different than gravitational potential energy? Well, other than the fact that it's missing off the energy, it has a different unit. So gravitational potential energy is measured in joules, as you'd expect. But gravitational potential is measured in joules per kilogram. Now that is a very interesting unit, because that's telling you that if I have a gravitational potential, it means instead of telling me what it actually has, it's telling me what I would have per kilogram in that field. So I'll explain what I mean. So I go back to this idea about a radial field. So say I've got a mass here, but I actually don't know what that mass is. Well, if I don't know what that mass is, I could say, well, what would the potential be at that point per kilogram? How much energy is it going to have per kilogram at that point based on that distance there? Well, the equation becomes very simplified once you understand the idea that instead of saying what you've actually got, you're saying what you would have per kilogram. We can say that because GPE is equal to GMM over R, well, we can divide both sides by the mass that we don't know. So GPE over M equals GM over R. Now, I'd just like to point out that this M here is this mass here, the mass that's creating the field. This is the same kind of appearance in field strength. The M in the field strength equation is the M of the mass that's creating that field. And obviously we've got R there. And there we have it. Look, that's joules per kilogram equals GM over R. And so what we've got there is we've got an equation for Vg, which equals to Gm over R. And that's where that equation comes from. Now, those of you who have a data sheet will be very observant and go, wait a minute, there's a negative sign in there. Where does that negative sign come from? Well, the negative sign comes from a very specific idea that you kind of need to ask yourself a series of questions, and I'll ask you those questions here. So I'm going to do it in a slightly different diagram down on the bottom over here. So say, for example, we've got our planet and we go to infinity. We go to infinity. Okay, so at infinity, technically, what is the field strength of this planet? Well, at infinity, it's going to have gotten so small because it's a radial field that's spreading with 1 over r squared. It's getting less and less and less. Because remember, field strength is proportional to 1 over r squared. That's because of the equation E is equal to Gm over r squared. If you don't know where that equation comes from, go back, have a look at some of the other videos. Obviously, you can say that's G, but sometimes we say E for field strength, especially when we're talking about electric field strength, but we'll come to that in another video. So at infinity, the field strength, G, is equal to 0, because it's not going to experience any field. So at an infinite distance, it's going to be 0. Well, if the field strength is 0, well, look back over here. We're not going to have any potential energy. It's not going to have any potential energy based on that field, and so it's not going to have any potential based on that field. So pretty much Vg at this point is 0 joules per kilogram, which means that is the highest value that it can be. That's the highest value, because the further you get away, it gets more and more and more and more. So how do we make this make sense? Well, all the values down to the surface of the Earth are negative. So hence why we have this negative sign over here. All the potentials in a gravitational field are negative, because it has the potential to fall back down this way, not go this way. It has the potential to become more negative. So that's kind of why we put that negative sign up there. So all values up to this point are negative, and hence that explains that negative sign. Okay, so let's talk a little bit more about the equations that you might observe here. So it's all well and good. We've got that potential equation, which is Vg is equal to negative Gm over R. Well, there are other equations for potential and actually work done, because we actually define gravitational potential as the work done by gravity in effectively per unit mass, work done by gravity per unit mass, to move the mass or object from infinity to that point. So what does that mean? Well, the by gravity, I think, is probably one of the most important aspects that you can take away from this, because by gravity means that gravity is going to have to pull in a mass that's at infinity. It's going to have to do work on it to move it from that point to that point. So here's our planet, here's infinity, here's our mass, and we've got to move it to that point there. So that means it's got to have that potential based on that R there. So it's the potential in moving the object from that point to that point is the potential that it has at that point. So it gives you an idea. It's a little bit of a weird definition, but it's the one we're going with, and it's one you need to remember and memorize. So yeah, it's the work done by gravity in order to use per unit mass required to move an object from infinity to that point. At that point is R. Okay, so that is the kind of definition of it. And actually we can use this work done idea to actually come up with another equation to help explain that. So the work done in moving between two potentials. So if work done is equal to that, well, look very carefully. So if we go back to, let me use a different clock here. If we go back to the idea that GPE is equal to GMM over R, well, you can effectively say that that's an amount of energy that it has, okay, an amount of energy that it has. And we can then rewrite this equation based on potential. So we can say GPE is equal to mgm over R. And the reason I've done that is because look what this term means. This term is potential. And so we've got an equation that we can rewrite this as GPE is equal to mvg at that point in the field. Well, that fairly makes sense because actually that's what I've already defined. But in your equation sheet, you'll notice that actually this is rewritten as work done is equal to mass times delta Vg. Because think about it. If I move from there to there, I'll have a change in potential. And obviously the mass, and I need to do work in order to move it from that point to that point. Or I might need to do work to move it from that point to that point. I've got to do work on it in either which case, whether it's gravity doing the work or me doing the work. So what we're doing here is we're saying, okay, a certain amount of work needs to be done in order to change the potential when the mass is that. So this little m here is the mass of the object that's moving around in this case. So that's all of the potential equations defined and looked at. Hopefully you found that helpful in describing all the things that go on in potential. I think the most complex thing for people to understand is this definition, but this definition is what it is for all intents and purposes. And when we look at electric fields, there is a definition similar to it that actually gives a little bit more context to it as well. And so watch that and see how it goes.